Today we'll be working on palindrome linked list problem. We're given a single linked list. The goal is to determine if this list is a palindrome. So first of all, what is a palindrome? A palindrome is something that if you read it forward, it will give you exactly the same thing as if you read it backwards. So 1, 2 is not the same as 2, 1. So this is not a palindrome. Whereas 1, 2, 2, 1 is exactly the same as 1, 2, 2, 1 if we read it backwards. So this is a palindrome. So another way to understand palindrome is that as long as the list is symmetrical with respect to the middle point, then it is a palindrome. And also an empty list is a palindrome. A list with only one item is a palindrome. Now we know what a palindrome is. How can we find an algorithm that determines if a list is a palindrome? The most intuitive approach is to follow the definition of the palindrome. If we can traverse the list forward and backwards and then compare the two results, then that is quite straightforward and simple. Well, the thing is that to do that, we need to put the traversal results into some kind of array and then compare the two arrays side by side. This requires big O of n space, even though the traversal is big O of n as well. Another approach is that we want to compare the front of the list to the back of the list, which means that comparing first item to the last item, second item to the second to the last item, so on and so forth until we reach the middle point. The thing with a singular linked list is that nodes are not randomly accessible. To be able to access any arbitrary node, we will have to do a traversal. Whereas if we convert the list into an array, then accessing items are constant time. So because of that, first thing we do is that we convert the list into an array, and then we can do this kind of front and back comparison. This is still a big O of n space complexity algorithm. Can we solve this without using any extra space? Let's take a look. For example, we have this list. Well, another approach is that if only we can split the list in the middle, we slice the list into two halves, and we somehow reverse the first half. So now we have two lists, and potentially they should be identical. Then we can start from the head of both lists and then do the comparison in parallel. How can we slice or how can we split the list in two halves? So we need to find the middle point of the list. Okay, so that reminded us of something called a runner-walker approach, which we use two pointers to so we use two pointers, one called slow, the other called fast. So fast moves twice as fast as slow, so which means that fast moves 2 steps forward each time, whereas slow moves only 1 step forward. When fast moves to the end of the list, as you can imagine, slow will be at the middle of the list. We not only need to find the middle point of the list, but also we need to reverse the first half of the list. The reversal of the list is quite simple. Each time before slow moves forward, we just need to change the next pointer of slow to point to the previous node, which means that we need to keep track of the previous node. Let's call that reverse, which starts at no. So in order to understand how this algorithm works and how the 3 pointers move in action, let's take a look at this in the context of our Python implementation. Here is our Python implementation. A list node is just a value in the next. Linked list is just a head and a tail and a size. Okay, moving forward. Now we will be focusing on this function called isPalindrome. Initially, we're initializing the 3 pointers to none, head, and head, which is exactly what's showing our list. Okay, first we do a check to see if fast and fast on next is not no. In our case, it's not. Then we get into our loop, And first, we move fast forward twice, which becomes the third node. Second, we change the slow down next pointer to point to reverse. So change this pointer to point to reverse. Okay, great. And now we change slow to become slow down next. So here, for those of you who are not familiar with Python's packing and unpacking feature, you might get a little bit confused here, because if slow becomes slow down next, when slow becomes reverse, well, here, this whole thing is called a tuple. So a tuple is an immutable data structure. So this data structure is created before the assignment happens. So these values in the tuple still takes on the original values pointing by these references. So this slow down next still points to this second item. So slow moves forward. Again, same idea. Slow here takes on the original value, which is the first items. This is why reverse can take on the first item of the list. So going forward, another round of checking fast moves forward twice, and then we change the pointer of next to become a reverse. Slow moves forward, reverse becomes the previous slow, and since fast is null right here, we break out of the loop and we're done. Here we do another round of checking. So this part is because the list right here is perfectly even, so we can split the list half-half without any problem. But what if we have an odd number of nodes? Then, for example, here we have an extra node. So what will happen is that we want to skip the middle node and do a comparison starting from the next node from the middle node. So this way we can compare apple to apple. For that case, we can do a check to see if fast is null. If it is not null, which means that we have an extra node, and we just move slow forward one more step. So after this, the comparison becomes quite straightforward. We use a loop, and we move the two pointers forward side by side. Whenever the values are not matching, we say this is not a palindrome. Otherwise, we get to the end of the two lists, and then we say this is a palindrome. Now let's do a quick check, recreate a list. So an empty list should be a palindrome. So yes, true. Now a list with one item, of course, a palindrome. Okay, great. Well, 1, 2 is not a palindrome, false. What about 1, 2, 1? An odd number of nodes, but also palindrome. Great. Even number. Okay, great. And not a palindrome, false. Okay, great. So now let's take a look at another approach to this problem. At the beginning of our tutorial, we talked about this kind of layered comparison approach, which is to compare, on the first item to the last item, second item to the second to the last item, so on and so forth. But that requires us to convert the list into an array, simply because of the nature of our singly linked list. However, a singly linked list is very recursive-like data structure, so that basically made us to think if there's a recursive way to solve this problem. So let's take a look at this recursion. What if we have a recursive function that starts at the first node, and we recurse down to the next node and all the way to the end, which is the last node, and then we recurse back. So on this level, we have access to D, which is the last item. What if we have a pointer that still points to the head of the node? Then we can do this comparison A and D, which is exactly our layered comparison idea, right? And then we recurse back one layer up. We have access to C. What if we also have access to B, which is the next node of A? Then we can do this kind of comparison on this level as well. And again, one level up, so this comparison gets crossed, which is okay. In our layered comparison in the array approach, we stop at a middle point, but in this case, we can keep on going, which is not going to be a problem, and this is just going to be a cross comparison all the way back to the end, to the outer layer. So how can we do this then? On each level, we would have to get hold of a pointer to the front portion of the list. That made us think if there's a way to use kind of a global variable to keep track of that, and at each function call we just move that global variable one step forward. And since stack, the call stack of this recursive function really is just a reverse order of traversing this list backwards, then these two can work side by side, which simulates the kind of layered comparison approach. So now let's take a look at this algorithm. We call this is palindrome recursion. And first we create a global variable called left, which points to the head of the list. Okay, and then we declare this helper function, which is really just where all the recursion happens, and it takes in a right pointer. So really is this. So this right pointer should always move forward until the end of the list. So here we say we are going to use the global variable left instead of making it a local variable. And the first thing we do is to create a base case to see if right is null. If it is null, then we just return to the previous call. Okay. And now we recurse down. And now we recurse down. If the recursion returns false, then we also return false. Then we do comparison on this level, move the global variable forward, and then we return true. So let's take a look at how this function works in action. So here we start by calling helper and putting left. Okay, so left is node A. So as we can see, first we get into this base case check. So first we do the base case check. So this is not going to be true until we hit the end of the node. So this is not going to be true until we hit the end of the list. And then we recurse down, so all the way down to the end of the list. And as to here, we can imagine that this will return true because this is going to, E is going to be null. And then once this returns, we can do the comparison between left and right on this level, our left is still pointing to A, but the right hand side is going to be D. So D comparing to A is true. Now here we move the global variable forward, so A becomes B. Okay, so here we do right and the left comparison. So our right on this level is going to be C, and the left is going to be B. No problem. Recurse back. We do a B and a C comparison, which is great. And at last we do A and a D comparison, and then we return true. So let's take a look at the time and space complexity for this algorithm. Time complexity wise, we are still doing a traversal, so this is still a linear time complexity algorithm. Whereas for space complexity, even though we did not use any auxiliary data structure to temporarily hold the members of the list, we still use the call stack for reverse ordering purpose. So this is still considered a linear space complexity algorithm. That's it for this tutorial. I'll see you next time.